Hi everyone, welcome to the 21st episode of Math and Beyond and this podcast. Today we are talking with Sownak Bose. He's an astrophysicist. He's an assistant professor at Durham University. Today we are talking about computational cosmology as this his research domain. And so I'm very looking forward to having this conversation. So I will now send him the invite and I will see you shortly. Hi, Sownak.
Hello, Francesca. How are you?
Hi, I'm doing fine. What about you?
I'm doing good. Thank you. Can you hear me okay?
Yes, it's great.
Awesome. How are things
Where are
going?
you? Sorry?
How are things going at your end?
Yeah, it's it's great. Here in Amsterdam, there are some windy days, so not the best as it is almost half July, and so yeah, maybe some more sunshine would be appreciated. But yeah, where are you at the moment?
I'm in Durham,
Okay.
which is obviously where I work. I've been traveling over the last 3-4 weeks, essentially, quite a lot.
Mm-hmm.
So it's actually quite nice to be home for a change, and have a fixed residence for a few days in a row.
Not being a nomad anymore. Okay.
Exactly right.
Okay, so I gave a small introduction about you, about the topic of discussion. You obtained your master in physics from Oxford, and you went on to PhD studies at Durham, where you are now covering the position of assistant professor. Is that right? At the Institute of Computational Cosmology, right?
Mm-hmm.
Okay, which is also the topic, our topic of discussion of today. And I would like to, start by asking you, indeed, what is computational cosmology? Because from the name, it sounds something that has not been here since the beginning of time, let's say.
Yeah, so I mean, computational cosmology, let's just try and break it down into the two bits of the word, so of the phrase. So cosmology is basically generally the study of the universe in its entirety. So rather than thinking about, say, just the phenomena and the physics that applies to our everyday experience in our galaxy, or just a set of galaxies nearby to us, cosmology is really interested in the study of the evolution of the universe as a whole. So right from where it began, how it then evolved, what it's made of, and ultimately, I suppose, what its future might look like as well. So of course, these are very grand questions that involve, well, by definition, basically everything in the laws of physics that we know of, over a very wide range of scales and over a very wide range of times as well. So significantly more than the lifespan of typical humans or even living organisms, really. So computational cosmology is essentially a way to try and approach this very complex problem of trying to understand the evolution of the universe over this very wide range of scales, using computers to solve what we think are essentially the important laws of physics and how they govern the things that the universe is made of, and therefore make predictions for what we think the universe might evolve like, assuming a certain set of laws of nature, or indeed a certain set of assumptions for what the universe might be made of. And computational cosmology then tries to take these predictions and compare it with the real universe, to get a sense of how well we've actually understood or not, as the case may be.
Okay, when does this field arise in the first place?
I guess it's kind of hard to pin down in some sense. So in some sense, astronomy and as a subject, or the study of the stars and the heavens as a subject, is probably one of the oldest scientific endeavors we have, right? And many of the things that we are trying to do, even in computational cosmology and astrophysics, basically are no different to the kinds of things people tried to do, thousands of years ago. I think really in terms of being a subject that you could actually compute things for, and computation being the important word, meaning that you can actually write down a set of definitive equations that you can then use to describe what you're seeing and then make predictions for what you might see in the future. I guess that, has its origins from Newtonian physics, so the time of Isaac Newton, who first described the ways to compute how two systems might evolve under the laws of gravity, for instance. And computational cosmology is then just essentially kind of broadening that into saying, okay, let's just not consider two systems interacting under gravity. Let's consider thousands, tens of thousands, hundreds of thousands, and so on and so forth. So I guess in some ways, the physical laws and the equations that are used have been around since the 16th century or whatever. Of course, with a little bit of refinement on exactly how we model these things. But in terms of how much of a mainstream component in terms of everyday modern research goes, maybe I'd say something that has really kickstarted in the 1970s or so.
Okay. What were in that period the first simulations taking place?
Well, I mean, so the first simulations in some sense actually took place even before the advent of computers. So 1970s became a sort of important time for this study, because that's when, I suppose, bigger computers were available more readily beyond just, the needs of, big government defense programs and nuclear testing reasons and so on and so forth. So that's why the 70s was important. But actually, in some sense, the first calculations in terms of what one might consider computational cosmology actually date back to the 1940s even. And famously, the first well-known example people will typically give you is the calculation of a Swedish physicist called Erik Holmberg, who was interested basically in understanding what happens when two galaxies essentially come close to one another and they interact under the force of gravity. And, I think the fundamental question he was interested in asking is, does one object capture the other object due to its gravity? And do these two objects have a mutual influence on one another? So this was a computational problem, which he approached by basically modeling each galaxy with a system of 37 points, 37 points each. So it's an n equals 74 problem in the n-body situation. But what's interesting here is that this is not points as you might represent in a graphical program on a computer today, or points as you might describe on a general computational setting, because there were no computers at the time to use. So what Holmberg did was actually to use light bulbs to represent these 74 different points, because he realized that light bulbs decay in the brightness and the luminosity with distance as 1 over distance squared, which is exactly what gravity does. So he realized he could actually mimic the effect of gravity from 73 light bulbs on the 74th one by basically looking at how the light received on this light bulb was affected by the presence of all the other ones. And so he basically drew this analogy between the intensity of the light received on the light bulb with the force of gravity essentially being exerted by these different point masses, which basically represent the distribution of masses in these galaxies, and then essentially move these light bulbs around based on how much brightness was being exerted at any given point. So that is basically your measure of gravity here. Then you can move it along based on Newton's laws. And then you evolve this whole system by basically physically lifting up light bulbs and moving them around, because there's no computers to do that for you. And what he got at the end was basically a representation of the so-called tidal interaction between these two galaxies. So he essentially predicted that as two, initially spherical systems come together and they interact under gravity, they will actually leave these tidal arms, which look like streams almost, which are essentially a memory or a remnant of their gravitational interaction, and form these spiral structures and so on, which were all predicted with the help of his light bulbs. And this is now, something that we see pretty often in much more complex simulations and even in real telescope images. So that really is the first simulation in some sense, which is not a simulation in any modern sense of the word, but is, I think, just a great demonstration of ingenuity.
Okay, you mentioned the name of the first type of simulation that I would like to clarify and dig a bit into it. What is the n-body simulation? What is it used for?
Yeah, so n-body, the n just basically is a reference to a number. So how many bodies or objects are interacting in a particular system that you're trying to model. So as I mentioned previously, the fundamental force of nature that people are interested in when it comes to cosmology, when it comes to the evolution of the universe, is gravity, which is, of course, well known thanks to Newton and Einstein. And the simple case of n equals 2, meaning that there's two particles or two objects that are exerting gravitational force on one another and therefore are evolving under each other's gravity, that system can be solved exactly. So you don't need computers for it. You can actually solve the equations using pen and paper. And those solutions were produced by Newton in the 16th century and allowed him to predict things like the orbits of planets around the sun. And the fact that when you solve this two-body system, you get elliptical orbits in the manner that we are familiar with in the solar system. The problem is, as you start increasing n, so you go beyond just two objects and go to 3 objects and then 4 objects and 5 objects, the problem gets more and more complicated. And actually, it turns out that beyond a system of just 2 objects, there is no analytic solution that you can write down, meaning that you can't just use pen and paper solutions to an equation to solve this problem. So you really need to start using computers to numerically solve it. And so an n-body simulation is basically a computer program you can think of that is solving the equations of gravity or whatever equations are defining your physical system for several objects that are mutually interacting with one another.
Okay. Why do you say that we are only interested into taking into account gravity in our simulation and we'll just leave aside the other 3 forces?
Right. Well, I mean, I think part of that is just simplicity, mostly because gravity is a very well understood force of nature, and it's a much more simple force of nature to model because, you can do this without invoking or needing to really understand quantum mechanics in some sense, at least gravity as we observe it. It is also the most important, I suppose, because it is an extremely long-range force. So, even though the gravitational force between 2 objects becomes weaker as the 2 objects move further and further apart from one another, it is still something that you can feel over distances that are astrophysically or cosmologically interesting. So the gravitational force of object A and object B exists over a meter, over a kilometer, over a few miles, and even over tens of thousands of light years. And you can compute exactly how that varies. So gravity in that sense is the most widespread and universally experienced law of nature. And we might end up touching on this later on, but it turns out that the vast majority of our cosmos is dominated, at least by mass, by something we call dark matter. And as far as we understand it, it is really gravity that is the fundamental force of nature that dark matter generates or produces in some ways. So it is the most important thing or ingredient that goes into sort of sculpting the universe as we see it today.
Okay. Yeah, we shall come to dark matter later. But now I would like to ask you, what is a Poisson solver?
Oh, sorry?
A Poisson solver.
Poisson solver, right. So what Poisson refers to is the name of a French physicist. And essentially he wrote down an equation which relates something called the gravitational potential. So you can think of it as essentially the gravitational field being generated by a particular object. And he said that that gravitational potential is described essentially by what is the distribution of mass around that object. So, thanks to Newton and Einstein and so on, we are familiar with this idea that whenever anything in the universe has a mass, so it's made up of stuff, it is able to exert gravity on something else. So mass generates gravity. So exactly how mass in the universe is distributed, whether it is spread homogeneously throughout the cosmos, or whether it has little lumps and bumps in different places, or if it is distributed in a very regular way or an irregular way, all of those different configurations will change what is the gravitational field surrounding this distribution of mass, and therefore how objects will move inside this field. So a Poisson equation is basically one that relates the gravitational field and basically how it varies as a function of space with the mass distribution surrounding it. So a Poisson solver is just basically a numerical algorithm. It's a computer program or some other technique that can be used to solve this particular equation, and therefore allow you to run an n-body simulation that will tell us how objects move in gravitational fields.
Okay. What is instead the particle mesh code?
A particle mesh code is basically a particular example of a Poisson solver. So as we were talking about in the beginning, a cosmological simulation is quite unique in the sort of arena of simulations, in the sense that you have a very, very large dynamic range that you're trying to solve the equations of gravity over. So you have processes on the scale of a few parsecs inside galaxies, all the way to tens of billions of parsecs, stretching many, many billions of light years across the cosmos. It turns out that if you were to simply apply Newton's laws and do, the 1/distance squared times the mass of the objects, and you were to sum that over many, many, many particles in your n-body simulation, that would essentially take infinitely long to do, because this is a very expensive calculation, and it becomes more and more expensive as you increase the number of particles in your n-body system. So there are a bunch of different approximations, well, not approximations, but different tricks and algorithms people use to simplify this process. And the simplest of these is something called a particle mesh algorithm. So what that basically does is, imagine you have a cube. This cube basically represents the size of your simulation. This is the random region of the universe that you are trying to model. What a particle mesh code does is that it takes all the points in this cube, which are representing the mass elements, or the dark matter particles, or the galaxies, or whatever, or the stars that are present in this cube, in this universe. And what it then does is then it converts this these sets of particles are basically representations of the overall distribution of mass in the universe, but it is in these discrete lumps, okay? Of course, in the real universe, we know that it's a much more continuous thing. So gravity it's not discretized in the form of big particles in a simulation, but you can think of it almost as a fluid. And so what a particle mesh does is that you create a grid. So it's just, breaking up your cube into a number of equally sized cells in 2 dimensions or 3 dimensions, depending on what kind of simulation you're running. And then you basically take these particles and you convert that discrete distribution into a continuous representation by essentially taking the particles and smoothing it onto this mesh. Okay, it's kind of like, think of making an image in some ways. Images are essentially, n by n arrays of pixels. And when you put all these pixels together and you apply some smoothing onto it, you can represent these individual discrete pixels into one continuous image. That's basically what a particle mesh is doing, is that it takes this mesh, think of the little cells of the mesh as being the pixels of your image, and it takes the little points and then smooths it onto that thing. And then once you've done that, you have basically a regular distribution of matter on this grid with which you can help actually solve Poisson's equation very easily using something called Fourier transforms. And Fourier transforms are basically very handy tools to solve complex equations like Poisson's equations, and the mesh representation of fields helps you really use Fourier transforms in a very simple way. So this particle mesh algorithm helps you solve Poisson's equation pretty accurately, very simply, using this sort of technique.
Okay. So this is basically just a technique that we can use in simulation. I would like now to cover some of the, let's say, proper simulation. And I would like to start from the hydrodynamic. What is it? Why we use it?
Yeah, so basically, remember I said at the beginning that the fundamental thing you care about in cosmological simulations is being able to solve the laws of gravity. Okay, and you very rightly pointed out what happens to the other three fundamental forces. Well, that's what hydrodynamical simulations try to do, which is that these are simulations where you don't just care about species that interact via gravity only, but so for example, the dark matter that we touched upon previously, but you also care about the other fundamental laws of physics, which we know affect the ordinary matter, the visible matter that you and I are familiar with. So the protons, the electrons, the hydrogen, the helium, and so on and so forth. So a hydrodynamical simulation is one that solves both the equations of gravity and the equations of hydrodynamics. So basically, how do fluids move, what kinds of conservation laws they obey, how they lose energy, how they gain energy, what kind of turbulence and viscosity is present in these fluids as they move through different regions of space. And then how gas, for example, then cools, eventually forming stars, and then how these stars evolve and blow up into the form of supernovae, create black holes, and all the other familiar processes that we know of in astrophysics. These are all elements that are captured within a hydrodynamical simulation, where you actually have the true baryonic matter, as we refer to it, present in there as well.
Okay, why, for example, do we want to use a hydrodynamic simulation? What do we want to simulate? And we usually use this type of simulation.
Ideally, I guess you're trying to simulate everything in the known universe in some ways. And the reasons why we use them is because we know that our universe is made up of more than just things that interact via gravity only. But we know that there's hydrogen gas, we know there's helium, and so on. We know stars form, and we know stars evolve, we know planets form, we know planets evolve, so on and so forth. So a hydrodynamical simulation really is, I would say, the most consistent way by which we can take these simulations or these virtual universes that we are trying to create on our computers and our supercomputers, and basically make a replica that can be most easily compared against the observed universe, because we are actually trying to take into account all of the complex physical processes associated with galaxy formation that occur over billions of years, and see what kinds of predictions they make for the distribution of galaxies that we observe in the cosmos, and what kind of structures and morphologies that they have. So the hydrodynamical simulation is, they can be trying to create whole, large populations of galaxies, or you can have specific classes of hydrodynamical simulations that try to create one or two very specific things, such as if you want to create a very detailed simulation that resembles the Milky Way, for example, because that's, of course, the galaxy for which we have the best data.
Okay. How does a hydrodynamic simulation differ from a large-scale structure simulation?
I mean, in some ways, they aren't necessarily mutually exclusive. So you can have large cosmological simulations that also have hydrodynamics in them. The complexity comes in the fact that, as I said previously, gravity is a relatively easily understood and easy to solve force of nature. And there are many efficient techniques that can be used to solve the equations of gravity on very large scales. When it comes to hydrodynamics, of course, the problem is that galaxy formation and the physics of the matter that we know very well is much more complicated, because you have to take into account not just gravity, but also the laws of thermodynamics, the laws of fluid dynamics, understanding of how stars form, how supernovae occur, how black holes operate, and so on, all of which are kind of approximate at some level in many senses. We don't have complete understanding of all of these things. So what that means is that you have to put in a lot of physical equations and a lot of techniques to solve these very complex processes. So that makes hydrodynamical simulations much more computationally expensive than a simulation that has gravity only, because you're basically having to do all the gravity only work plus all of these new things. And so doing hydrodynamical simulations that also are extremely large and extremely detailed, so have high resolution, meaning that you can study the physical processes on small scales. Simultaneously doing both of those is very challenging, just in terms of just computing power, really. And so typically some kind of compromise is made, which is that you either, you lose a little bit in terms of the resolution capability of your simulation by having bigger volumes, or you have smaller volumes, meaning that you have, fewer objects to study and maybe a less representative simulated universe to look at, but you can afford higher resolution and study the galaxy formation processes in more detail.
Okay, but in all of this simulation, how do you set, let's say, the initial condition of a simulation? So how do you, how do you adjust the parameters? How do you obtain an initial value for these parameters?
No, that's a great question. So there's a few different points to this particular answer. So initial conditions are very important because, of course, once you have a set of initial conditions, the right set of initial conditions, ideally, followed by the right equations that describe the evolution of that system, that's really all you need in order to be able to make a fully consistent prediction of how that system is then going to evolve. Now, you might ask, okay, how do we know what the initial conditions or what the state of the universe was like right at the beginning? Because that is, looking at a time that was 14 billion years ago, beyond the accessibility of present telescopes and so on. But actually, and this maybe sometimes surprises people, knowledge of the initial conditions of the universe, of our universe, is one of the things that astronomers and cosmologists have measured with more exquisite accuracy and precision than most other data sets that are available to us. And that is thanks to something that we call the cosmic microwave background radiation. So in a few words, what that is basically, this is the radiation that was generated at the time of the origin of the universe, if it is the Big Bang. And that radiation, basically in the form of photons, then streams towards us over the course of the 13.8 or 14 billion years or so. And you can think of these microwave background photons essentially as being kind of like messengers, in that they carry with them a memory of what the structure of the universe was like when they were initially liberated. And so by taking satellites that measure the microwave background radiation, examples being the COBE satellite, the WMAP satellite, and the Planck satellite, which we've used over the last 30 years or so, we can actually map the distribution of the microwave background radiation across the entirety of the sky. What we actually measure is basically how hot or cold these photons are in terms of temperature. And we can create this very high accuracy, very exquisitely detailed map of temperature fluctuations, which you can map directly to what the density fluctuations or the lumpiness of the universe was when it was only 400,000 years old. There's a little bit of mathematics that basically relates the temperature that we measure now to the density distribution then. And this lumpiness in the initial distribution is what then eventually collapses over time through gravitational instability and creates the very complex structures that we see today. So these microwave background experiments actually tell us very, very accurately what the initial conditions were. Specifically, it tells us about 6 numbers, which define, how much matter there is, what is the strength of these amplitudes and fluctuations, what is the amount of dark matter to ordinary matter, so on and so forth. So that is kind of well understood. What is less well understood, I suppose, is exactly what the detailed properties of, say, the dark matter is. It tells, the microwave background radiation tells us about how much, gravity sourcing dark only matter is relative to the amount of ordinary matter, but it does not tell us about the specific physical properties that dark matter can have, because the microwave background radiation is measured on much, much larger scales than the scales on which differences in the properties of the dark matter will make differences in the predictions of galaxies. So in that case, what we have to do is actually make different choices for what these physical properties could be by maybe talking to particle physicists who might be able to give us insights from a different perspective. And then we try out these different possibilities, run our simulations, and evolve them up until the present day and actually see how similar to the real universe these simulations look like. And if it looks very different, we can then see, what aspect of our assumptions is making that effect.
Okay. And talking indeed about dark matter and then dark energy, how do we hope, we know these are very, let's say, exotic stuff that we do not fully understand, but how do we hope to model and understand these these two things together?
So I think, in many ways, this is the holy grail of cosmology, which is trying to understand each of these two things that we think dominate the energy content of our universe, that we think are highly influential in making the universe look like it does today. And this question that you ask, which is, how do we hope to understand better? I think, my perspective at least is that I think it's very unlikely to me that by just working as a theorist or as someone working in computational cosmology alone, you will ever really be able to make a very definitive level of progress to this question. And what I mean by this is that I think any level of advancement or progress towards answering these questions of what could dark matter be, what could dark energy be, or what could they not be, relies very much simultaneously on the development and advancement of our observational techniques. So, how complex or how, high resolution are our telescopes or our ways of observing the universe at very early times using things like the James Webb Space Telescope, or using, telescopes that we have on the ground and in the Earth and so on. Because what observations do is that they allow us to, as we keep improving them, of course, is that they allow us to open up a view into new uncharted regimes of our cosmos that we might not have been able to see before. And as you start opening these doors, you slowly begin to hopefully try and find cracks in your understanding of the universe. So perhaps you observe some phenomenon that you might not have seen previously. And then when you try and look into your theoretical models and your numerical simulations, you try and see, okay, do we see these features in our simulations as well? And you find that, oh, actually, this doesn't seem to be predicted in my simulations or anyone else's. Then that becomes an interesting problem. And then you can actually try and see, okay, what is it about my model that is making it unable to predict this? And what do I need to do to change around my theory of dark matter, or this theory of dark energy, which tells us about how fast the universe grows and why it accelerates in its growth? what do I need to change those things in order to be able to explain these new observational results? And so how we make progress in these questions is basically by having detailed theoretical predictions of the universe, and predictions here is the important thing, because a particular model of dark matter or dark energy will be able to predict exactly what we are able to see now, but also what we might hope to see 10, 20 years down the line. And then when the observational capabilities are equally ready, and then we can test these models further and then hope to make progress on that particular question.
Okay, but for example, like dark matter, we can measure quite, let's say, precisely the effect that this type of matter has on the matter that we can then see. How do we then take this type of matter into account during our simulation? Meaning, how do we simulate dark matter, then dark energy?
Yeah, so for the dark matter, at least from everything that we have observed so far, all the phenomena that we've seen, it seems pretty clear that, well, if dark matter exists, and I think we have good reasons to believe that there's something like that dark matter that does exist, then it is something that interacts primarily through gravity. Okay, so it may have very, very tiny other interactions through the fundamental forces of nature, such as electromagnetism or the ability to scatter off one another and so on. But to all intents and purposes, any evidence of that seems pretty small. Okay, so you already have a very narrow range of possibilities of what you need to model, which is you need to model a species that does not have electromagnetic interactions. Otherwise we would see it. And B has gravitational influence. And so that becomes a very simple thing to do. But you mentioned, we have the ability to see the effect that dark matter has. But actually you can then see, then what about the effect that dark matter could have on the things that we do not see yet? So what do I mean by this? So one really good example of this stuff is looking at the distribution of galaxies by their size or their brightness or how heavy they are in terms of stars. Okay, so before say 20, 30 years ago, at which time we had the advent of big galaxy survey programs like the Sloan Digital Sky Survey and so on, we knew of, say, a handful of galaxies that surround the Milky Way that we call the satellite galaxies of the Milky Way. Okay, so they kind of orbit the Milky Way kind of in the same way that planets orbit the sun. And they, in terms of their brightness and their mass, tend to be quite a lot less massive than the Milky Way. So different models of dark matter will make different predictions for how many smaller galaxies actually will orbit a bigger galaxy like the Milky Way. And that is often the case, that as you change around the properties of dark matter, you typically end up changing around distributions and properties of galaxies on very small scales. The reason why this is the case is because on large scales, in terms of the large scale structure of the cosmos, we have very high precision observations. So therefore, there is a lot of constraint on what dark matter cannot be. It cannot be something that changes around the predictions on very large scales, because otherwise that would be just ruled out completely. And in fact, in the 1980s, when people were first interested in the question of particle dark matter, they considered the idea of neutrinos, which are these like particles which are essentially dark in the sense that they don't really interact with photons in that sense. And they have this particular property that they're very light, so they zip around the universe at near the speed of light. And people did simulations of universes where the dark matter was assumed to be neutrinos, and they found that the prediction for the distribution of galaxies over large scales looked completely different to what was actually observed by telescopes. Okay, and so this clearly couldn't be the right model of dark matter, because it was already inconsistent with observations. And so what you can then do is basically change around properties of the dark matter and see at what point the thing becomes inconsistent with observations. So for example, we were talking about these little tiny satellite galaxies around the Milky Way. Previously, before SDSS and the Dark Energy Survey and so on and so forth, we had limited knowledge on the number of tiny satellites orbiting the Milky Way. And therefore, we had a much wider range of possibilities for what the dark matter could be, because many models of dark matter predicted the existence of the Milky Way and a handful of relatively bright satellites surrounding it. But as we have then gone to discover more and more and more, basically our telescopes have become much more sensitive, we've been able to identify much fainter galaxies that previously evaded our detection. And many of these tiny, fainter galaxies would not have been predicted by some models of dark matter, because in those models, low mass galaxies basically never form in the first place because of just how the dark matter operates in the early universe. And so as we have gathered more data over time, we have actually excluded a very wide class or wide range of possibilities for what the dark matter could be in terms of its physical properties. And that's basically how we end up, making progress on this subject, which is we try and think of what is the realm of possibilities and then basically move our theoretical calculations in lockstep with how the data is progressing and basically see how the data can then help us inform our calculations better.
Okay. What is the type of dark matter that, say, at the current moment better explains the evolution of the universe and formation of large-scale structure?
Yeah, so there's a particular class of dark matter models that is called cold dark matter, which is, I would say at this point, the sort of front runner for what we think is the most realistic, quote unquote, description of dark matter in the universe. And by realistic, I mean it seems to make predictions that are most consistent with the data that we observe. So what cold dark matter is basically the assumption that the dark matter is made up of tiny particles, which are subatomic in nature, and they're just like protons and electrons, except that they are not predicted in the standard model of particle physics. Cold dark matter particles are collisionless, typically, meaning that if you have two dark matter particles, when they fly past one another, they'll just go through each other and go through us as well. So they don't scatter like little billiard balls. And the cold here essentially refers to how fast these particles were moving in the very, very early universe. So the cold here is a reference to kinetic energy, because there's in physics, there's this analogy between the speed of particles, their total energy due to that motion, and therefore the temperature. This is typically something that is applied to thermodynamics and things like cups of coffee or anything that has temperature associated with it. So that analogy has just been brought forward into the dark matter category. So cold dark matter is basically any set of theories that encapsulates particles that are moving at very low velocities in the early universe, in contrast to the neutrino models that we were talking about previously, because the neutrino models, by virtue of being almost massless, people in fact thought that they were zero mass, just like photons. They move around the universe at the speed of light, or close to the speed of light. And so they actually come under the class of something called hot dark matter because they move very fast. And this hot dark matter scenario or idea was ruled out very quickly by comparing with observations of known galaxies at the time. And so people then went to the opposite end to think of, okay, let's think of a hypothetical class of dark matter particles where they don't move at the speed of light, but move at a completely negligible speed. And that's where the cold stuff came from. And that turns out to be rather a good description for most of the observed phenomenon that we've seen so far.
Okay. You mentioned before the Sloan Digital Sky Service and the Dark Survey and the Dark Energy Survey. While making my research for this conversation, I understood how actually important these surveys are, but I would like to ask you why. What do they provide us about the universe, and also how do we, let's say, try and interpret that, meaning how do we analyze that?
Yeah, so let's. I mean, I think the way that they inform us are a little bit different, I suppose, for the Sloan Digital Sky Survey and the Dark Energy Survey. I mean, their ultimate goals are kind of similar, but the way they go about it is a little bit different. I think generally the main unifying theme of both of these types of surveys is to use telescopes present on Earth to make detailed maps of the distribution of galaxies in the universe. Okay, so when I say detailed maps, I mean you hope for not just the two-dimensional location of an object on the sky, but actually a three-dimensional information on that particular question, which is not just, if you think of this as a coordinate system, not just the X and Y location, but also the Z position. And that three-dimensional information actually is what is key about these things. And the way that they have really helped us is to enable us to understand how galaxies are distributed, in the cosmos, and what is the pattern of this distribution? Is it random, or does it actually have some kind of structure to it? And if it does, then does this structure sort of evolve in time, or has it always persisted or become more randomized as time progresses, and so on? So the Sloan Digital Sky Survey, for example, is known as a redshift survey, meaning that the redshift is basically this third coordinate that we are talking about, which is identified by basically looking at how the spectral lines in galaxies shift as a result of their motion in the sky. And SDSS, as it's known for short, has helped make these three-dimensional maps going out to fairly large distances, and enabled us to basically quantify and measure the evolution of the galaxy distribution over time. And what we found is that galaxies actually aren't just randomly distributed on the sky, but there's actually a very clear sign of clustering and a very clear pattern in how they are actually distributed. And you can then use your n-body simulations, for example, to see whether the process of gravitational instability, i.e. the process through which regions of the universe that were slightly lumpier eventually became lumpier still due to the gravitational attraction, or regions that were empty early on became emptier still because matter flowed out of those regions to fill in the more dense regions. So basically over time, you kind of create this contrast in structure all over the cosmos. You can use n-body simulations to predict how that structure evolves and see whether it actually then resembles what we observe in the galaxy distribution measured by SDSS and other surveys. And actually, when I mentioned previously that in the 1980s, people found that the neutrino universes, didn't look like what the true universe seemed to look like at that time, that was based on the true universe there was based on something called the CFA redshift survey, which was one of the earliest catalogs of galaxy redshift. So it was in some ways a predecessor to the SDSS project. So SDSS came some 20 years later and obviously enhanced that catalog in quite a significant way. Okay.
Also, I believe you previously mentioned it. These surveys should serve us as, let's say, in trying to understand and grasp better what are the parameters, the values of the parameters that we should input in our simulation, right?
Yeah, exactly. So, I mean, actually, we get a fairly good handle of what some of the cosmological parameters should be just through measurements of the microwave background radiation. It turns out then we can actually reduce some of the uncertainties on those parameters, even though they're very small already from the microwave background radiation, by using the constraints on the same parameters from things like SDSS and the Dark Energy Survey and so on and so forth, because they're ultimately measuring the same things, i.e. how lumpy the universe is, how much dark matter there is, how much ordinary matter there is. The key difference being, of course, is that the microwave background radiation is looking at stuff in the very early universe, whereas the galaxy redshift surveys like SDSS and DES and so on are looking at the very late time universe, i.e. the universe after 14 billion years of evolution. And ideally, you would hope that the cosmological parameters that you measure with the early time measurements like CMB and the late time measurements like SDSS look similar and that they're consistent. And if they don't, that's when you start to find interesting things. Then you say that, why is it that my measurement of, so say there's a parameter called sigma 8, okay? It's just essentially is a measurement of how lumpy the universe is, okay? Just how much matter there is along any particular direction or whatever. You can get a measurement of that from the CMB. You can actually get a measurement of that from other, present day observations through things like gravitational lensing and so on. And what we find actually is that these two numbers don't always agree with one another, depending on exactly how the test has been done. And then that begs the question is, why is it that they don't agree with one another? Is it because there's something about one of these two methods that we haven't accounted for, that if we did account for, you'd actually be able to find that these two methods are actually consistent with one another? Or is it because physics is fundamentally different in the early universe compared to the late time universe? Okay. And these are examples of things called tensions in cosmology. And a particularly prominent, so the sigma 8 one is a very prominent one. Another very prominent one is the so-called Hubble tension, which is a statement about the measurements of the expansion rate of the universe, either through the CMB or through late time observations like looking at supernovae near to us. And actually, when people compare these numbers, they seem to be off at a level that is statistically significant. And it's currently not fully understood why that is.
Okay. So after we talked about the surveys, I would like to go on to the proper simulation. And I was kind of struck by one simulation, which was the Millennium simulation, when I read into it and I saw the images. Because the images that came out truly looked like sort of the neural structure of a brain. So what is this Millennium simulation? What did it, let's say, what was the purpose of the simulation and what we actually understood from it?
Yeah, so the Millennium simulation was a project that was carried out through the joint effort of a number of institutions. The primary ones being the Max Planck Institute for Astrophysics in Germany, and actually Durham University as well, so where I work. This was a little bit before my time, so the simulations were performed in 2004, with the papers ultimately being produced in 2005. And it was, I would say, probably one of the first great examples of a really high fidelity simulation of structure formation over a large cosmological region. By a large cosmological region, I mean a region that spans, several hundreds of megaparsecs. So really looking at the largest scales corresponding to the large scale structure of the universe, that would be measured by things like the Sloan Digital Sky Survey, for example, but simultaneously had a lot of resolution. In other words, a lot of n-body particles in it as well, that will allow you to study the fine-grained detailed structure of the cosmos as well. So you simultaneously get large volume, but also detailed structural predictions for the distribution of dark matter on small scales, which is important, of course, because these are the regions where galaxies form inside these things called halos of dark matter. And so the Millennium simulation basically had more than, I think, around 10 billion particles involved in it. And it was really quite a monumental achievement in its time. So it relied both on the development of very efficient codes for solving these equations. So by 2005, these methods that we talked about, like particle mesh and so on, were incorporated into an n-body code called Gadget. And actually, it uses more than just particle mesh. It uses a couple of other techniques in it as well to get the forces over very large scales. So it involved the development of these codes, but also the presence of powerful computers to solve these codes on, to run these codes on. So it uses supercomputers to do this work, thousands of CPUs basically working together to solve this problem. So it was quite a monumental computational feat getting it, and you're correct in saying that when you look at the images of the cosmic web that it predicts after, the 14 billion years of evolution, it is very much like what one thinks of as being like the neural networks in one's brain. I don't know if there's any underlying reason for that, but that's just what it looks like. And we call that the cosmic web. And one of the things, so you asked previously, what is the model of dark matter that people think is the appropriate one? And we talked about cold dark matter then. So this Millennium simulation was a simulation of cold dark matter. And one of the reasons why the cold dark matter model has become such a preferred model and such a successful theory is because of many of the predictions made by the Millennium simulation for eventually stating what is the distribution of galaxies in the cosmos look like, how many galaxies of a particular mass should we be able to observe per unit volume of the universe, so on and so forth. How do the distribution of star-forming galaxies differ from the distribution of galaxies that are not star-forming, for example? All these kinds of detailed questions that you can then predict once you have a cosmological simulation. You can then look at real data, such as the real distribution of the clustering of galaxies in the Sloan Digital Sky Survey, and see, does the predictions of the Millennium simulation look right? And in fact, many of those things came out to really unprecedented levels of accuracy, which is why we think that, even though we don't know what the dark matter is, we know that it has to look at least approximately something like cold dark matter, because otherwise we wouldn't be able to make these predictions look the way they do in the real universe.
Okay. What do you think quantum computers can achieve in the future cosmological simulation? What do you expect from this quantum computing revolution to bring forward for cosmological simulation?
It's kind of hard to, I suppose, make any definitive predictions on that until one really fully is able to realize what is the I suppose, true potential of quantum computers and what they can achieve. At the moment, the way quantum computers are, they're really nowhere near capable of doing the kinds of problems that we're interested in, because, they're able, some of the more sophisticated ones are able to do relatively rudimentary calculations that, an ordinary calculator or a computer is able to do very easily as well. In principle, of course, if the promise of quantum computing is met exactly by what people have been saying, and it is met by the technology and so on and so forth, perhaps one thing it will enable us to do is to overcome this challenge that I mentioned to you previously about this compromise between the size of the simulation and how detailed a calculation one is able to afford in terms of the resolution of the simulation as being a sort of computational hurdle. So ideally, in a quantum computer setting, you might think that anything that requires a normal CPU, several thousands of floating point operations or computations to think about, a quantum computer is able to do that in essentially an instant. So your ability to solve the equations of gravity over a very large range of scales and the equation of hydrodynamics and so on will be near instantaneous. Of course, there's now a couple of issues with that. One being that, well, firstly, none of our computer programs at this point are really built to make use of quantum computers. So you would have to actually rewrite all of these methods that we've talked about, like particle mesh and so on and so forth, in a way that is actually making use and making advantage of quantum computers. And that kind of thing is not new, because every time new technologies, new chips, new GPUs, and these things come around, people do have to modify the way computer programs are written to make the best use of these things. I guess the other problem, of course, is that quantum computers don't necessarily help you with the other challenge you have with running very big simulations, which is just fitting in a lot of stuff into the memory of the computer. So computers are limited by how much memory you can, or basically how much data you can hold in at any given point in time. And so you also have to find a way to, address that. But ideally, if you can use quantum computers to speed up your whole computational process, then maybe the advantage is the environmental upside to all of this, that actually you don't need to run simulations for many hundreds of millions of hours producing several tons of CO2 all the time, because you'll just be able to do it much more efficiently. So in that sense, I suppose it's good at a societal level. But we'll have to see what the true promise is. Who actually knows at this point?
Okay. I would like to ask you one other, let's say, more personal question, opinion. Sometimes I wonder about the fact that we talk about quantum mechanics, theory of the very small, and then we go on to general relativity, which we, let's say, apply to our cosmos, so theories of the very large. And if you think about it, the theory of the very small, quantum mechanics, applies at scales which are 10 to the minus 30, 40, like numbers which are extremely small. But if I also think about theories of the very large, or cosmological theories, this also involves numbers which are astonishingly large. When you for example, in the Millennium simulation, I remember there was also a scale of some gigaparsec, and gigaparsec is an extremely huge amount of kilometers, which are numbers that we humans cannot really understand. We can say, yes, it is trillions and trillions and trillions of kilometers, but we don't really understand what the number is. Don't you find that it is quite ironic, let's say, quite a coincidence that we humans capable of understanding our surrounding, we are in the kind of precise middle, in the sweet spot, that we do not understand the very small, we do not understand the very large, yet we can deal and make a precise statement and description in both regimes.
Yeah, no, I mean, I think that is an excellent point, and I completely agree. And I think that's a great testament to the advancement of humanity and our effort to try and make sense of the universe around us, that as I don't even know if we are truly in the middle of that sweet spot or not, but offset somewhat to one side or the other. The fact that we can make sense of these extremities of scales is really quite astonishing. And I think that kind of in some ways tells you about the power of I suppose the development and the evolution of the subject of physics. The fact that prior to Newton, the physics as a subject was really the metaphysics and these sort of more ethereal questions of our existence and our place in the cosmos, and really translating this into some kind of less of an art form or a philosophical form into something that is quantitative and that is robust and that is testable. That is thanks to people like Galileo and Newton and so on, and everyone who's come up after them. And in many ways, you have to kind of say that the fact that these relatively simple models for describing the universe around us, the fact that they do such a phenomenal job in helping us explain the kinds of phenomena that we see, must tell you that at some level we must be somewhere on the right track, right? So we can't be too far off from the truth if we are really able to explain this enormous range of scales. And this is particularly evident in, I think, the case of the quantum world, where quantum mechanics is probably the best tested theory of physics that we have, in the sense that it makes very, very detailed, precise predictions beyond the level of precision that I think any other physical theories have been able to do. And you can measure exactly what the energy levels of a hydrogen atom are to an incredible and extraordinary level of accuracy. And all of that then feeds into the kinds of applications that quantum mechanics has been used for, like the development of transistors and radios and blah, 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 and so on and so forth. And that's not to say that, your theories can't get refined, and it is necessarily the end of our progress, because as we've seen from general relativity, for example, general relativity kind of says that Newtonian gravity works supremely well, given these sets of conditions, but it isn't the final theory of gravity, but it is maybe a subset of a much grander set of principles that then boils down to Newtonian gravity in the regime that Newton was actually concerned by. So in that sense, it was perfectly right. But if you care about really not just things being accurate to 1%, but to 0.0001%, then you need something a little more sophisticated, and you need an evolution in your thinking. And that's kind of, I guess, where I think we're going in cosmology as a subject as well, which is that we think we understand the parameters of our universe, or even the nature of dark matter and dark energy, to a pretty good level of 5-10%, maybe even better. But really that last few percent, or that extra push that takes us from the sort of Newtonian regime to the Einsteinian regime of understanding the cosmos is really what will make the difference in terms of what we truly understand by dark matter and dark energy and these other ethereal questions.
Okay, hopefully you may come back again, telling us of some further understanding that we can dig into our theories. So Sownak, I think we can wrap it up here. Thank you very much for your time and your explanation. I am personally extremely fascinated by these topics. I find them among the most, I think, elegant in our, let's say, science world. So thank you very much. It was very exciting.
Thank you, and it's been my pleasure to talk to you as well. So if we wanted to resume this discussion at some point in the future, we can obviously do that, hopefully with maybe more exciting updates to share with you as well.
That's awesome. So thank you, Sownak, and thank you everyone for following along with us. This was Math and Beyond, and I will see you in the next episode. Ciao.